My name is Megan Cordill. I'm from the Erich Schmidt Institute of Material Science of the Austrian Academy of Sciences. I have a memory of being at the kitchen dinner table with the TV on and my mother watching the news, and I'm seeing the iconic footage of people on the wall, around the wall, and celebrating. So as far as I can remember, I watched it on television. I actually wanted to be an artist and a sculptor, for that matter, and so my parents actually got me into ceramics, and so I was throwing pots on a wheel and sculpting things with ceramics. My mom then saw an article in a Japanese journal about the Japanese making ceramic engines, and she goes, "Megan, you need to be a ceramic engineer," and I'm sorta am now. You get to use both sides of your brain and you get to be creative. When we're designing our new material systems, we do have to think outside the box, where maybe we're not interpreting something, but we're using information to create something new. So it's a little bit like being an artist. The funny thing about my research is that instead of breaking things, I actually try to make things unbreakable. So with my work, we were able to make, for example, glass ductile. But also in other work that I do on flexible electronics, we're able to use materials engineering to actually design and create new material systems that are unbreakable to mechanical bending. Well, we work on very small things, so we're looking at materials that are on the order of a few nanometers to maybe a few microns. That's actually smaller than one single hair. So we're looking at very, very small quantities of material, and that means that we need to use high resolution microscopy methods, such as the microscope behind me, to actually see the materials that we make and to see how they actually break or deform. Some of the new findings we found for especially glass, which was making glass ductile, this was led by an international team, where we found that using experiments and simulations, we could prove or at least visualize that when we start to mechanically deform glass, what's happening atomically is that the bonds are switching with different atoms, and that's what makes it ductile. So, do you like your smartphone? Do you want your smartphone to be able to bend? That's one of the ways that we can see where our research is going. We want to be able to make unbreakable flexible electronics, both in the glasses that we use, but also in the microelectronics or the hard components that we use to our flexible electronics, as you can see here. We want to see those things become unbreakable so they are more long-lasting and so we don't have to make them as much. So one of the special fields is actually in medical devices or wearable sensors. Right now, there are some devices that are available for athletes to wear so they can monitor their hydration, or even for newborn babies or those babies in the ICU, intensive care units. They need special monitoring all of the time. And this will allow them to wear the sensors, but still be held by their parents while they're actually growing and recovering from their birth. The plastic island in the ocean is one thing that does keep me awake, which is why I'm passionate, I guess, about making our flexible electronic devices more sustainable. Currently, I am working on polymer systems that are non-recyclable. They are very hard to recycle, but we need to use these materials first so we can understand what makes the materials unbreakable, so then we can apply this to a new generation of bioplastics. So my parents were actually the reason why I'm an engineer. They both kind of steered me in this direction, and also why I'm a material scientist. My whole family knows that I break things, and that I break things very, very, very small. And so that's all they need to know. One of these days, maybe they'll buy something that I actually studied.